Hi everyone. In this video, I'm going to be going through gas stoichiometry problems. So at this point, it's assumed that you have learned about gases and the various gas laws, and you've learned about stoichiometry. So this isn't really something new. It's just combining two concepts you've already learned before in maybe a way you haven't seen. So let's make sure we're good on what we need to know about gases, so the various gas laws. The most common gas law you're going to encounter with gas stoichiometry problems is the ideal gas law, which is PV equals nRT. The most important value here to have memorized is R, which is the ideal gas constant. There are many values of R, but the one we use as a Chem 1-2 program is 0.0821 liters times atmospheres over moles times Kelvin. Now, how do we just pick that value? Well, if you use liters, atmospheres, moles, and Kelvin, that's the number. If you change the units, it's going to change the value. So that's the value of R that we use. And these four units in R dictate the units you must use for this gas law. So in other words, if you're going to use this gas law, your pressure must be in ATM, your volume must be in liters, your moles must be in moles, and your temperature must be in Kelvin. So that's the ideal gas law. You might come across a little combined gas law. That's the ones and twos. That's when you have a gas that's not changing conditions. Sorry, I said that wrong. That's when a gas is changing. So if you're heating a gas up, if you're shrinking a gas, if you're pressurizing a gas, that's when you're going to use combined. So P1V1 over T1N1 equals P2V2 over T2N2. You can also write this without the denominators. P1V1 T2N2 equals P2V2 T1N1. Okay. Now with this gas law, there's only one rule you have to follow, and that's temperature must be in Kelvin. Any other unit is fine as long as it matches. For example, if you have P1 and P2 given in the problem, you can't plug torr in on one side and PSI on the other. They have to match. You might also come across that new gas law, which is Dalton's law of partial pressures, which basically states that the total pressure, PT, or P total, is the sum of the partial pressures in a gas. So, you know, every gas around you, I mean, air right now is about 78% nitrogen. The nitrogen is exerting a partial pressure of about 0.78 atm on you. The oxygen gas, which is 21%, is exerting a partial pressure of about 0.21 atm on you. The idea is every gas exerts a partial pressure. Every gas within a mixture of gases. Okay, this comes into play anytime you're collecting a gas above water or through water displacement or by bubbling a gas through water. So look out for some of those clues. You'll often find yourself subtracting the partial pressure of water from the total pressure to get just the pressure of the gas you want. Don't forget STP. STP standard temperature, 273.15 Kelvin. Standard pressure is 1 atm, aka 760 mmHg, or 760 torr. Okay, and also don't forget that at STP, 1 mole of any gas equals 22.4 liters. That's something you can actually use as a conversion factor. I call it the STP shortcut if you want. All right, so without further ado, let's get to one of these problems. Potassium metal reacts with fluorine gas. What volume of fluorine gas at 17 degrees Celsius and 683 torr is required to react completely with 20.7 grams of potassium? So in a gas stoichiometry problem, you're often going to be using a gas law, and it's usually PV equals nRT. And you're going to be doing stoichiometry, sometimes in that order, sometimes in reverse order. Let's look at what's really happening here. We're solving for volume of this gas when it gives us this temperature and this pressure. It gives us the mass, not of the gas, but of potassium. So if we're solving for the volume of a gas and there's no changing temperature, changing pressure, this is going to be a Pivnert problem, PV equals nRT. So we're solving for volume. That's what we're solving for. The problem gives us temperature, check. The problem gives us pressure, check. We know R, check. What's missing? N. It doesn't tell us how many moles of gas we have, but it does tell us how many grams of potassium we have. How do you think we're going to take grams of potassium and get moles of fluorine gas? Stoichiometry. So that's where the stoich comes into play. You're often going to be using stoich to get a value for N and then plug it into the ideal gas law, or maybe in reverse order. Maybe you'll use the ideal gas law to get N and then run it through stoichiometry to find like grams of something. So what we're doing here is we're going to write out our balanced equation, K solid plus F2 gas yields. Sorry, I was expecting this to be a single replacement. It looks like it's going to be a synthesis. So let's assume these come together and form potassium fluoride, which would be aqueous. I guess that would be solid if there's no water involved. The state's not important here. Okay, so we balance this with a 2 here and a 2 there, giving us a 2:1:2 mole ratio. So the problem says we have 20.7 grams of potassium, 20.7 grams of K, and we're going to use stoichiometry to answer the question of how many moles of fluorine are needed to react with that. And then we're going to grab that mole value, N, and plug it into Pivner. So potassium, 39.10 grams. 20.7 divided by 39.10 gives us 0.529 moles of potassium. Check out the mole ratio from here to here. It's a 2-to-1 ratio, so I'm going to divide that by 2, which gives us 0.265 moles of F2. And just like that, I have N. And now we just solve for V. So V equals nRT over P. That's me just rearranging the ideal gas law. I basically just got P out of there. Okay. Volume is going to equal 0.265 moles. That's N. 0.0821 liters times atmosphere over moles times Kelvin. That's R. I'm going to try to squeeze this in here. T is temperature, but you can't plug in 17. You have to turn it to Kelvin. So 17 plus 273.15. The 0.15 will get cut off. That'll be 290 point to keep it as a whole number. 290 point Kelvin. And I'll divide that by pressure. 683 torr. I can't plug that in either. That has to be in ATM. So 683 divided by 760 gives us 0.899 ATM. And that goes down here. Okay. Let's see. Mole cancels mole. Kelvin cancels Kelvin, ATM cancels ATM. I'm left with liters, which makes sense. 0.265 times 0.0821 times 290 divided by 0.899 gives me a final answer, 3 sig figs work, of 7.01 liters. There we go. And by the way, why do I use 3 sig figs when it gave me 17 degrees? Doesn't that limit me to 2? No, because notice I never plugged 17 in. I plugged in the Kelvin version of that, 290 point. And that's in fact why I put that point there, was because that's a whole rounded to the ones place. Okay, next problem. Oxygen can be generated in the lab by heating potassium chlorate, KClO3. So here we have the balanced equation already done out. What mass of KClO3 must be used in order to generate 5.00 liters of oxygen, measured at 17 degrees Celsius and 1.21 ATM? Well, we're looking for mass of KClO3. We're given the balanced equation. Clearly, we're going to have to use some stoichiometry here. Okay? Now, in order to find how much KClO3 we're going to get, so that's like where our X is going to be, it tells us about the O2. Now, normally, the problem would give you like grams of O2, and you would just turn it into moles, run it through the grid, and get your answer. But it didn't tell us the grams of O2. It gave us the volume of O2, the temperature, and the pressure. So what do you think you're going to do here? We need to find moles of O2 to then do the stoichiometry. Well, hopefully you're yelling at your screen, ideal gas law, PV equals nRT. We're going to use the ideal gas law to solve for N, grab this N value, which is moles of oxygen, plug that in here, use stoichiometry to find moles of KClO3, and then take that value and find our mass. So it's kind of like the opposite of the last problem. In the last problem, we started with stoichiometry to find moles, then plugged that into Pivnert. Now we're starting with Pivnert to find moles, running that through stoich. Okay, let's solve. So starting with the ideal gas law, PV equals nRT, we're solving for N moles. N equals, so I got to divide RT out of there, PV over RT. Pressure is 1.21 atm. That's the unit we need. Volume, 5.00 liters. Very generous problem to give us those. R is 0.0821 liters atmosphere over mole Kelvin. And T is 17 degrees Celsius, which must be turned into Kelvin. So the same as before, 290 point Kelvin. Okay. ATM cancels ATM, liter, liter, Kelvin, Kelvin, we're left with moles. 1.21 times 5 divided by 0.0821 divided by 290. I got 0.254 moles. And what is that moles of? Is that moles of KClO3? No, that's moles of the gas. Okay, we plugged in the liters of gas, the temperature, the pressure. So that's going to be moles of O2 gas. And a real quick aside here. If you're going to plug these four numbers into your calculator, be warned. In your denominator, you have to either do this one step at a time, like I prefer doing, where I would say like 1.21 times 5.00 equals, divided by 0.0821 equals, divided by 290 equals, or you got to put this in parentheses. If you just plug it all in straight up with no parentheses, your calculator will end up multiplying by the 290 and you'll get the wrong answer. So be careful with that. All right, so we used Pivnert to find moles of O2. We're now going to plug this in right here. And we're going to use stoichiometry and the mole ratio to go from O2 to KClO3. So it's a 3:2 ratio. So however you do your ratios, if you use the conversion factor method or dimensional analysis, I personally would notice a 3:2 ratio is 1.5 times smaller. So I'm just going to divide 0.254 divided by 1.5, which will give me, divided by 1.5, is going to give me 0.169 moles of KClO3. Problem mass for grams, just got to do a little bit of molar mass calculation. So K is 39.10, Cl 35.45, 3 O's is 48. I got 122.55, which gives us a final answer of times 0.169, 3 sig figs, 20.7 grams. Okay. Next one. In one method of producing aluminum chloride, HCl gas is passed over aluminum and the following reaction takes place. So it looks like we have another balanced equation there. What volume of HCl at 4.71 atm and a temperature of 43 degrees Celsius is needed to produce 837 grams of aluminum chloride. Classic molarity-stoichiometry problem. I can already, or not molarity-stoichiometry, gas stoichiometry. So what are we solving for? We're solving for volume. Is our gas undergoing like a temperature change or a pressure change? No. So we're going to be using PV equals nRT. This is going to be very similar to our first problem we did, I can tell. We're solving for V. What do we know about our gas? We know the pressure, right there. We know the temperature. What else do we always know? R, it's just a constant. What do we not know? N. How are we going to find N? Stoichiometry. So notice the problem gives us 837 grams of AlCl3, aluminum chloride. Using this and using our balanced equation, we can turn this into moles of, now which gas? Because we have H2 and we have HCl. HCl. So we need to use this to turn it into moles of HCl. And then we're going to plug the moles of HCl right there in for N. Okay, so let me start with a molar mass for AlCl3. So 26.98 plus 3 chlorines, 3 times 35.45. And that gives me 133.33 is the molar mass of AlCl3. I divide my grams by that molar mass, which gives me, 837 divided by answer gives me 6.28 moles of AlCl3. Okay, 6.28 moles. Make sure we did that correctly. Yeah. I feel like that G shouldn't be a G. I think I typoed that. It's probably solid. Anyway, so that's our moles. We're looking for volume of HCl. What's the mole ratio? 2 to 6, also known as 1 to 3. So what am I going to do to this number? I'm going to triple it. 18.8 moles. So my 6.28 moles of aluminum chloride come from 18.8 moles of HCl gas. And that's the number I plug in for N. Okay, so, yes, I plug it in for N to solve for volume. So V equals nRT over P. V equals 18.8 moles times R, which is 0.0821 liters atmospheres over mole Kelvin. T is temperature, which is 43 degrees plus 273.15 gives us 316 Kelvin. And I divide that by pressure, 4.71 atm. Looks like, I'm checking my units, mole, mole, Kelvin, Kelvin, atm, atm. We're left with liters. All right, let's see what we get. Three sig figs, 104 liters. Okay. A 250 milliliter flask of hydrogen gas is collected at 763 millimeters mercury and 35 degrees Celsius through displacement of water. A little bell just went off in my mind. Did it go off in yours too? Something I mentioned at the start of this video. Whenever I talk about displacement of water or trapping a gas through water or over water or like bubbling a gas through water, I'm thinking Dalton's law. I bet that's going to come into play. The vapor pressure of water at 35 degrees Celsius is 42.2 mmHg. Vapor pressure in this context is the same as the partial pressure of water. Again, ding, 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 Dalton's law. How many moles of H2 gas are in the flask? So do we have a changing gas? No. So this is not going to be combined. This is going to be PV equals nRT. We're looking for moles. What do we know? Well, It tells us the temperature, 35 degrees. We know R, of course. We know volume, 250 milliliters. What's going on with pressure? It gives us two values. Well, we need to know the pressure of the hydrogen gas. What it says is you collect this gas at this pressure, but through water or over water or through displacement of water. If you collect a gas through water, some of that gas is going to be water vapor that you need to account for and subtract it out. According to Dalton's law, total pressure is pressure 1 plus pressure 2. These are partial pressures and so on. Now, in this case, the total pressure is the pressure of the H2 gas, which is what we're looking for, plus the pressure of the H2O gas. Now, that's also given in the problem. So through Dalton's law, we're going to take 763 millimeters mercury. That's going to equal the pressure, not HP, pH2, plus 42.2 mmHg. And really what this means is we're going to subtract out that partial pressure of water. So 763 minus 42.2 is going to give us our pressure of H2 gas, which is what we need. 763 minus 42.2 gives us 720.8. And the unit is mmHg. Okay. So back to our Pivnert. Notice we're not actually using stoichiometry in this problem, so maybe it doesn't quite fit in this video, but I think it's important. All right, solving for moles. So N equals PV over RT. N equals my pressure, which is this one down here, after you subtracted out the water. Oh, not that yet, because you can't plug in mmHg into the ideal gas law. We need to divide that by 760 to convert it into ATM. And I get 0.948 ATM. Okay, so that's my pressure. Volume, 250 milliliters. Can't plug that in either. That's going to be 0.25 liters divided by 1,000. Divide that by R, 0.0821 liters times atmosphere over moles times Kelvin. And divide that by temperature, which is 35 degrees. We add 273, we get 308 Kelvin. ATM cancels ATM, liter cancels liter, Kelvin cancels Kelvin. We're left with moles, which makes sense. Let's see what we get. 948 times 0.25 equals, divided by 0.0821 equals, divided by 308 equals 9.37. I'm going to call it 9.4. And my unit is moles. That doesn't seem right. I think I messed something up. I did. 0.948. Whoops. My parenthesis covered up my point. So I assume it's going to be 1,000 times smaller than this, but let me double check. 0.948 times 0.25 equals, divided by 0.0821, divided by 308, 0.00937 or 0.0094. There we go. And the unit is moles. Now, how did my instinct kick in that I've said something wrong? I know that 1 mole of gas is 22.4 liters at normal conditions, it's STP technically. If we're going to end up with 9.4 moles of gas, that's going to be like 10 times that. That's going to be like 250 liters of gas. So when I looked up here and saw 1/4 of a liter, I knew something was wrong. And in fact, now it makes perfect sense. We ended up getting like a lot more than that. That would end up being like 25 liters or so. Or no, yeah, 250 liters. Makes sense. Okay, I got one more. If 142 grams of tricarbon octahydride, aka propane, combust, what volume of carbon dioxide gas at STP will be produced? So we're looking for volume. Okay, do we have a change in gas? No. So again, PV equals nRT. We're solving for V. By the way, we've solved for V a lot. You can also solve for other variables. I just happen to write these problems or find them from worksheets in ways that ask for volume a lot. I could have just as easily asked for the pressure of carbon dioxide. Well, I guess I told you STP here, but anyway, we're solving for V in this case. Let's see what it gives us. It only gives us one number, but it does tell us STP. By telling you STP, it's really telling you two things. That tells us the temperature and it tells us the pressure. So right there, we're given temperature, we're given pressure. We know R always. So what are we missing? N. How are we going to find N? Stoichiometry starting here. Let's do it. Balanced equation. Combustion of tricarbon octahydride. That's going to be C3H8 plus O2 gas yields CO2 gas plus H2O, which is generally liquid or gas depending on the reaction. Let's call it gas for now. Balanced equation, I need a 4 here for my H's. I need a 3 here for my C's. 3 times 2 is 6, 4 times 1 is 4, 6 and 4 is 10, so 5 there, giving me a 1, 5, 3, 4 ratio. All right, let's take our grams, 142 grams of this. I need the molar mass, so 12.01 times 3 plus 8 times 1.01, so a molar mass of 44.11 grams. 142 divided by 44.11 gives us 3.22 moles. Okay, we're looking for carbon dioxide gas. What's our mole ratio? It's 1 to 3. So what do? Triple this. 9.66 moles of CO2 gas. We've now solved for N. You can now plug in into PV equals nRT. You can plug in N. You can plug in temperature, which is 273 Kelvin. You can plug in pressure, which is 1 atm. You can plug in R, 0.0821, and you can solve for V. Or you can use the STP shortcut. We're at STP, right? Remember we said earlier that at STP, 1 mole equals 22.4 liters of any gas? Well, I can just take my moles of gas, multiply it by 22.4 liters per mole. Remember, this only works if you're at STP. This does not work for every problem, but because we're at STP, we can do this. 9.66 times 22.4 with 3 sig figs, 216 liters. And if you had solved this using Pivner, you would have gotten the same answer. Okay, so that does it for this. Good luck with the gas stoich problems, everyone.